Hello everyone, this is module M4.5A covering mirrors. The A is because I am going to break it into two videos due to the large amount of material. In module M4.2, we talked about reflection. We learned that the law of reflection states that the angle of the reflected ray, as measured from a line that is normal to the surface, will always be equal to the angle of the incident ray. We also talked briefly about flat or plane mirrors. When you see an image in a plane mirror, you are detecting rays that traveled from a light source to the object, bounced off of the object to the mirror, and finally found their way to your eyes to be interpreted by your brain as an image. Your brain, however, does not realize that the rays it received are the product of all of this bouncing. The brain sees an image that is formed where the rays of light would have come from had they traveled in a simple straight line. This means that the brain interprets the image as being behind the mirror. The dashed lines that represent what the brain interprets as a straight line path for the light beyond the mirror are called virtual rays because no real light rays actually travel behind the mirror. The real rays, of course, are the ones that reflect off of the mirror from the real object. Because the image that the observer sees is formed by virtual rays, the image itself is called a virtual image. The law of reflection still applies to curved surfaces. The normal line is perpendicular to a line that is tangent to the surface, and the angle of reflection still equals the angle of incidence. So to find the angle of reflection for a ray of light bouncing off of a curved surface, first, find the point where the light reflects. Second, draw a line tangent to that point. Next, draw the normal line, which is perpendicular to the tangent. Measure the angle of incidence from the normal line, and then finally draw the reflected ray, ensuring that the angle of reflection as measured from the normal equals the angle of incidence. If the surface has too many curves, the reflected light will scatter in every direction as it reflects, resulting in no image. This is why reflective surfaces are usually smooth. However, curved surfaces can still be smooth. If the curvature of the mirror reflects light in enough of an orderly way, images can still be perceived, but they might be distorted. In the example pictured here, the light rays reflecting from the man's fingers still travel more or less together to form a discernible image of a hand, but the spacing between rays is altered by the curve of the mirror, making the size of the hand compared to the rest of the image disproportional. Parts of the image that reflect from one part of the mirror seem too big, and parts of the image that reflect from another part of the mirror seem too small, due to differences in the curvature of the mirror at different places. If the curve of the mirror is regular enough that the rays reflect in an orderly and predictable fashion from all parts of the mirror, a coherent image can be formed. The entire image might be too small or too large, but the parts of each image are still reasonably proportional. There are two basic mirror shapes that are often used to produce coherent, correctly proportioned images: spherical and parabolic. Spherical mirrors are mirrors that follow the curvature of a circle or sphere. Usually, spherical mirrors are not a complete sphere, but if their edges are extended 360 degrees in every direction so that the sphere is complete, the curvature at all points would draw out a perfect sphere. Spherical mirrors have two sides. On one side, the spherical mirror is concave. On the other side, the spherical mirror is convex. Spherical mirrors have some important key quantities. The center of curvature, C, is located at the center of the circle or sphere that would have been drawn if the mirror continued through 360 degrees. The center of curvature is located at a distance of exactly one radius of curvature away from any point on the spherical mirror. For the purposes of most ray diagrams, the pole or vertex is located at the center of the mirror itself. But the actual location of the vertex on the mirror depends on the location of the observer. Here, observer 1 is located on the horizontal line, so the pole that observer 1 sees will also be on the horizontal. Observer 2, however, is off horizontal. The images seen in the mirror by observer 2 will therefore depend on pole 2 instead. The principal axis is a straight line that passes through the center of curvature and the pole or vertex. Usually, the principal axis is drawn horizontally so that points on the principal axis can be thought of as coordinates on the x-axis. Of course, if we've changed the location of the observer, then the entire frame would have to be rotated in order to align the principal axis with the horizontal again. The focal point is located exactly halfway between the center of curvature and the pole or vertex, so you can find the focal point with the equation F equals R over 2. Let's see how light rays reflect off of a spherical mirror. We will start with the concave side. First, let's select a point on the mirror for our light to bounce off of. We draw a tangent line at that point, and then we can draw a normal line that is perpendicular to the tangent. Now we can start drawing rays. Each incident and reflected ray obeys the law of reflection, so the angle of incidence has to equal the angle of reflection for each ray we draw. If the incident ray is traveling along the principal axis, it just reflects off of the vertex and goes straight back along the principal axis where it came from. For any light ray that reflects off of the mirror at the vertex, the principal axis itself is the normal line. This makes it really easy to draw the incident and reflected rays. Now let's look at the rays that bounce off of an object. For simplicity, we will just consider the point at the very top of the object. Of course, many light rays will bounce off of the tip of the object in all different directions, but 4 specific rays are particularly useful in determining where the image of the object will be formed for an observer on the principal axis. These rays are the principal ray, which is incident parallel to the principal axis, reflects off the mirror, and then passes through the focal point. The central ray, which is incident at the vertex. The focal ray, which comes from the tip of the object through the focal point and then reflects off of the mirror so that the reflected ray is parallel to the principal axis. And the radial ray, which comes from the tip of the object, passes through the center of curvature, and continues on to the mirror. When it hits the mirror, it reflects back in exactly the same direction that it came. If you have a steadier hand or more artistic talent than I do, then all 4 of these rays should converge on a single point. This point is where the tip of the image of the object will be formed. You can see that the focal ray and the parallel ray are, in a sense, the reverse of each other. The parallel ray starts out parallel to the principal axis, reflects, then passes through the focal point. The focal ray starts by going through the focal point, reflects, and then ends up parallel to the principal axis. This means that at some point in time, both the parallel ray and the focal ray are parallel to the principal axis. This will become important later when we talk about spherical aberration. There is one catch to all of this. The focal point is defined as the point exactly halfway between the center of curvature and the vertex of the mirror. But it turns out that rays that are parallel to the principal axis do not always reflect exactly through the focal point. You can see on this diagram that the 2 rays that are closest to the principal axis intersect fairly close to the focal point. But as the rays get further and further from the parallel axis, this intersection point moves further and further away from the focal point, towards the vertex of the mirror. The inconsistency in where these rays intersect results in an unfocused image. The phenomenon of parallel rays not converging at the focal point of a spherical mirror is called spherical aberration. Because focal rays also end up parallel to the principal axis at some point, focal rays are also subject to spherical aberration. This photo shows significant spherical aberration. The overall layout and content of the photo is clear, but the details are out of focus. As we increase the radius of curvature, the same length of mirror will look flatter. the intersection points of the parallel rays will start converging towards the focal point. When the radius of curvature is very large compared to the length of mirror, the parallel rays do reflect through a converging focal point. Thus, spherical mirrors with a large radius of curvature compared to the length of the mirror experience less spherical aberration. One way to quantify this relationship between the radius of curvature and the length of the mirror is to look at the angle formed between the top of the mirror and the bottom of the mirror and the center of curvature. You can see that this angle is much smaller for the mirror with a shorter length compared to its radius of curvature. Therefore, mirrors that represent a smaller angle's worth of the circle have less spherical aberration. Once this angle is small enough, the mirrors experience negligible spherical aberration. When we treat a spherical mirror as though there is no spherical aberration, we say that we are using the small angle approximation. Unless otherwise stated, for the remainder of this course we will assume the small angle approximation is valid, even if we draw mirrors with exaggerated radii of curvature in order to make it clear that they are spherical and not plane mirrors. I will cover more of the properties of concave spherical mirrors in more detail in the next module, which I am splitting off from this one to keep the video shorter. For now, let's move on to another type of concave spherical mirror. A second type of regular curved mirror is the parabolic mirror. Instead of tracing the arc of a circle, a parabolic mirror traces a trigonometric function, the parabola. Parabolas are actually mathematically centered around a specific focal point, which guarantees that every single parallel ray, no matter how far from the principal axis, will reflect back to a single exact focus point. But don't worry, we're not going to have to do any of this math. The key idea for you to remember is that parabolic mirrors are shaped like parabolas in order to obtain a single precise focal point for any parallel ray. Parabolic mirrors focus all the parallel rays onto a single focal point. This can be very useful if you need your image to be very precise. For example, parabolic mirrors are often used in precision astronomy to detect distant stars or galaxies when we need to collect as much of their faint light as possible. Usually, the detector for such rays is placed exactly at the focal point in order to maximize the amount of light they can collect and focus. Shown here is the James Clerk Maxwell submillimeter parabolic telescope located in Hawaii. It detects infrared and microwave light from distant galaxies. A more down-to-earth application of parabolic mirrors is a parabolic cooker. Remember how we talked about light carrying energy? A parabolic mirror doesn't just focus the light rays, it also focuses the energy that those light rays carry, which can be released as heat. A parabolic cooker is a large parabolic mirror that can actually be used for cooking. In the resources section, I posted a video showing a parabolic cooker lighting leaves on fire, just from the focused heat of sunlight on a relatively cool day. So if parabolic mirrors have better focus, why do we even bother with spherical mirrors? Parabolic mirrors have issues of their own. If the observer is not exactly on the principal axis, parabolic mirrors are subject to something called lateral distortion, because the exact focus of the parabola depends on the rays that the observer is seeing being parallel. For precision applications like astronomical telescopes or parabolic cookers, where the user places the detector or the meal exactly at the focal point, the user doesn't need to worry about what the light rays are doing for external observers that are not on the principal axis. But for common mirror uses, where a human being needs to have a reasonable, undistorted field of view from various positions, this lateral distortion can cause problems. The mirror shown here is parabolic, and the picture is taken from some point that is just a little bit off of the principal axis. You can tell that the reflected image is probably a group of trees, and the edges of the leaves and other objects in the image look pretty well focused. But it is difficult to discern much more than that due to the severe lateral distortion of the image that makes the trees seem to swirl around the edge of the mirror. Spherical mirrors are also much cheaper to make, as they are symmetric about the center point, so it is easy to manufacture them. As long as their length remains fairly short compared to their radius of curvature, spherical aberration is minimal, and images in spherical mirrors are sufficiently focused for most everyday purposes. The photo on the right shows a concave spherical mirror, with the photo shot from about the same angle as the parabolic mirror on the left. But because of the spherical symmetry of the mirror, most of the image in the spherical mirror has no lateral distortion. The spherical concave mirror also has a small angle of curvature, so the spherical aberration of the closer objects is minimal, although the trees in the background are still a bit fuzzy. Spherical concave mirrors and parabolic mirrors are two examples of concave, regular mirrors. Because the rays all reflect inwards towards a focal point, both types of mirrors are referred to as converging mirrors. Converging mirrors focus light and focus images, and can make images that are larger than the objects that they are reflecting. This makes them useful for many purposes where humans want to see an object more closely, such as shaving or cosmetic mirrors, or dental instruments. Converging mirrors are also used in car headlights to focus the beam. Another type of regular curved mirror is the convex spherical mirror. Convex spherical mirrors have all the same parts as concave spherical mirrors: the center of curvature, the focal point, the vertex, and the principal axis. These parts, of course, are still located inside of the curve of the circle, but now the object, the rays, and the observer are outside of the circle. We can still draw the same four principal rays with some slight modifications. Now, when we draw the parallel ray, after its reflection, instead of going through the focal point, it goes directly away from the focal point. The central ray acts pretty much like you would expect. It hits the vertex of the mirror and reflects off so that the angle of incidence is equal to the angle of reflection. The focal ray for a concave mirror is supposed to go through the focal point before reflecting. But obviously, since the focal point is on the other side of the mirror, this is impossible for a convex mirror. So instead, the focal ray aims towards the focal point, but it hits the mirror before it gets there and reflects parallel to the principal axis. Similarly, the radial ray aims towards the center of curvature, but it hits the mirror and reflects before it gets there. Since the radial ray is already perpendicular to the tangent of the mirror, it reflects straight back the way it came. Now obviously, these four rays will never converge. But just like the brain will interpret the rays from an object seen in a plane mirror as traveling in a straight line to form a virtual image behind the mirror, the brain will also extend the principal rays reflecting off of a convex mirror to the other side, where they do all converge. Thus, the image formed in a convex mirror is always virtual, it is always upright, and it is always smaller than the object. If the object moves closer to the mirror, the image gets larger. If the object moves further from the mirror, the image gets smaller. You can experiment with convex mirrors at the GeoGebra interactive animation linked in the resources. Because the real rays reflecting off of the convex mirrors do not converge, convex mirrors are also called diverging mirrors. You can have convex parabolic mirrors as well, applying the ideas of parabolic concave mirrors to the convex side, just as we did here for spherical mirrors. Because convex mirrors can form images from a very wide field of view, they are often used for security, allowing store owners or front desk personnel to see entire rooms with a glance. They are also often used at corners and intersections to allow drivers to see around obstacles. In summary, we've learned that flat or plane mirrors create virtual upright images that are the same size as the object. We learned that curved mirrors bend and distort images, and that regularly curved surfaces can distort images in predictable ways. Concave mirrors can focus light and magnify images, and convex mirrors shrink images and provide a large field of view. We also talked about parabolic mirrors and how they focus images precisely, but they experience severe lateral distortion. Spherical mirrors experience much less lateral distortion, but they are subject to something called spherical aberration, where mirrors with either a smaller radius of curvature or a longer arc length do not have a single precise focus point, and therefore images in these mirrors can be blurry. We also introduced the key features of spherical mirrors: the principal axis, the center of curvature, the focal point, and the vertex or pole. The principal rays that are used to determine where an image is formed are the parallel ray, the focal ray, the central ray, and the radial ray. The image is formed where these rays converge. That's all I've got for this video, but in module M4.5B, I will talk a little bit more in detail about the properties of concave spherical mirrors.